Arun sir, shall we start, sir?
Yes, I'm ready.
So today I would like to welcome Arun Iyer sir for this fifth day session. Sir, welcome you, sir.
Thank you.
I would like to welcome our beloved HOD, Dr. Praveen J. sir. Sir, welcome you, sir.
Thank you, sir. Thank you.
And also I welcome all the participants of this Atal FDP. And also I want to inform that today a feedback link will be shared as part of the FDP. So please fill up the Google form and that will be shared in the chat box soon. Thank you. Sir, over to you, sir. Arun, sir.
Okay, thank you. Yeah, I've just started sharing my screen. Let me know when it's visible.
It's visible, sir.
Okay, thank you. Hi, I welcome you all for the day 5 session. So today's focus is going to be on static timing analysis, the basics of it, and very preliminary basics of CMOS power related concepts. I mean, I wanted to cover both the topics, but I think while I was creating the content, I found that I couldn't fit in the power optimization and related aspects which I wanted to cover today in today's session, because there were a lot of content related to static timing analysis which had to be included. So what I plan to do is that there's going to be a small change in the agenda for today. Static timing analysis will be covered as usual, as was planned yesterday when I shared the agenda. And for power, we will today talk about some very basic aspects, some simple concepts of dynamic, static power, basically the leakage, short circuit power, and what are the variables and aspects related to that. And then I think once we discuss that and we end today's session, tomorrow I will cover the optimization and for power performance area trade-offs on digital logic, and some examples for optimizations which we could do at various levels, at circuit level, at a design level, at architecture level, at system level, and so on. Tomorrow, it appears we may have a very packed session. I hope to cover all of it, but certainly I will focus on the topics which are shown at the top here. The ones below are fairly advanced topics. I wanted to cover them, but if let's say I run out of, let's say I'm not able to pack all these contents in the time allotted, then I think we will skip it. I'll share the slides. Maybe the audience can refer to this content offline, and maybe they can reach me through the organizers and if they have any questions. So tomorrow we're going to cover, as I said, these two top items, and additionally concept of Moore's law, and then a very important concept which is Dennard scaling, which is one of the reasons why we've been able to scale VLSI aggressively, slowing down on the Moore's law, as you may have been hearing. Problem with wire scaling, interconnect, power challenges, and then as you may already know, a lot of these SoCs or chips which are built these days have a lot of processor cores or GPU cores. It's not a single core anymore. So we'll talk about that and this, and a related law called Amdahl's law, which is, we will cover that. So these topics which are advanced, I'll try to pull in the FinFET concept at the top. That's probably relevant. But the other ones we'll see, I think, if we can cover. So this is the agenda for the next 2 days. And let's start with today's items. So we've been talking about we talked about combinational logic, combinational actual gates, which were physical implementation of combinational logic. And then we showed how they could be built using transistors. We talked about delay aspects, transition time and delay time. We talked about sequential elements, their timing aspects. And then yesterday we even talked about specifically focused on characterization. That means how we could measure some of these timing aspects and create the timing database called .lib, right? So now, as we saw yesterday, the timing database or the .libs are very useful for running a lot of steps in the design flow, synthesis, um, placement, clock tree design, and then routing. So, and then finally, when all of these things are completed, we have to check whether the timing specs of the design are being met. So timing specs specifically mean we keep hearing about 5 gigahertz, 4 gigahertz, and so on for various CPUs and GPUs running at 2 gigahertz or 3 gigahertz and so on. So these gigahertz numbers are nothing but the performance or the clock frequency spec. So we need to check whether we can meet the performance spec. So setup timing is primarily the check which is used to check for performance. There are a lot of different names for it in the academia and sometimes in the industry. It's also called max timing. Max means maximum delay or maximizing the delay. So setup timing is checking for performance, whether we are meeting the performance specs or not, whether the clock which is being provided to the sequential elements is able to run at the spec'd frequency or not. Hold timing, if you remember yesterday, as I said, hold check or hold time was basically checking whether the sequential element is able to hold on to its state if there is a data which is trying to disturb the existing state. So this is basically not a performance check, but more a functional and a reliability check, whether data is reliable and functional properly. So this again there's a separate check for this, and sometimes this is also called as a min timing check because we are trying to speed up the data. In setup, we are trying to slow down the data. In hold, we are trying to speed up the data. So it's also called min timing check. And then there could be additional checks. Clock gating checks. I didn't talk about clock gating yet. We'll probably touch upon that tomorrow in some power optimization options. So clock, as we've been discussing, it's a very active signal. It runs, it's basically in theory, a free running signal. Free running means it's always running up and down, which means it's running at a fairly high rate. And which means if the clock is running at a very high frequency, there's a lot of power consumed by the whole clock network. All the nets which are receiving the clock network is going to consume a lot of power because it's switching at a very high rate, very frequently, right? So it draws power, discharges power, draws power, discharges power. That's how a clock signal works, right? And it is essential for reliable working of sequential elements. So the clock is an extremely critical signal, but also if you're pushing for performance, let's say some of the recent Intel and AMD CPUs are going beyond 5 gigahertz. That's a significantly high clock frequency, and a huge amount of clock power is being consumed. So clock gating is one of the methods by which we can try to cut down unnecessary clock activity. If let's say if a register doesn't need to switch its data from D to Q, that means in that case, in that scenario, we don't need the clock to toggle. So in such cases, we can use a clock gating circuit to block the clock from reaching the sequential element. So there is a timing check for that, and that's called the clock gating check. There are some specialized checks called false path checks, async checks, multi-cycle checks. These checks are something which we will skip in this talk because this requires some advanced understanding of timing, and I'm not sure that all every individual in the audience understands will get this, since we only talking about basics of static timing. So I'm going to skip these three, but feel free to bring this up if anyone in the audience has some idea about it. I can discuss this during the break. So we're going to focus on setup timing, hold timing, and clock gating checks. As I said, I'll reiterate. Setup timing is going to check for performance, whether the clock is able to hit the right performance spec or not, whether the design will hit its performance spec, which basically means whether the clock is able to run at a high frequency, which you have decided upfront or not. Hold is whether is a more a functional or reliability check, whether data is going to work, whether the data held by the sequential elements is going to be reliable or not. That's very important. Even more important than performance, because why? If we have a setup problem, which means the clock is unable to run at the spec frequency, let's say you're not able to run at 5 gigahertz, so what? We can run it at 4.8 gigahertz. That's a slight drop in performance, but still fairly acceptable for most customers. Even if that fails, okay, let me run it at 4.5, 4 gigahertz. I can basically means that if I have setup timing problem, I can slow down the clock and I can ensure that the chip is still functional and working. But if I have a hold timing problem, there is no way I can get the chip to work. So it is an extremely important, more important than a setup timing check. And hence, companies put a lot of effort in ensuring they don't really have any hold timing issues in the way they run the analysis. So very important check here. Clock gating, again, an important check, but it's something which comes into play only if you're trying to save clock power. Okay, so setup timing, right? Let's talk about that. So this is a very simple, let's say a simple design, or basically a part of a design, or could just be the whole design. There is a register here, a flip-flop, another register, flip-flop, FF1 and FF2. There is some combination logic sitting between them. This could be a chain of gates. This could be maybe some simple just a chain of inverters or buffers. It could depend on what kind of logic it is. Depends on what's implemented here. We don't know. So it's just been abstracted by this box here. And so if it's a sequential system, which means there has to be a clock signal. So we have a clock going to both the registers. When I say registers, it means a flip-flop. Flip-flop and registers are used interchangeably. And so if I say register, it should mean flip-flop to you. Don't get confused if you think it's something different. It basically means the same thing. So if I have flip-flop or a register, then I need a clock signal, and that's a clock signal here. And if there's a data signal, obviously, because a sequential element requires a data input. This could be coming from something else or coming from the chip boundary. And then the output of this register is now going through the combination logic. That is, this state of this register is being used by taking it through the combination logic and passing it as input to the next register. Now, this interaction between two sequential elements, flip-flops or registers here, this thing is called a timing path. Now, if a clock has a waveform like this, which is usually what's considered when we're running any digital analysis, simple square waveform, the clock time period is going to be the time from the edge A to the edge B. Edge A is when flip-flop 1 is trying to capture and send out its data. Edge B is when flip-flop 2 is going to capture or send out its data. Right? Now, let's continue. So if I look at this, as I said, the cycle time, the time period of this, the separation between A and B, these 2 points in the waveform is the time period. And let's say that time period is T. What is the basic requirement for this circuit to work? or this circuit to meet its performance, the cycle time, that means this whole window, this window is the time during which the whole computation of by the logic should happen. What does that mean? The computation means that the clock arrives on the flip-flop, it sends out the data from the output. That's called the clock to Q. That means that's the output delay, clock to the output delay. If you remember, we've been talking about clock to Q for the last 2 days. So clock to output delay, this delay, that means some time taken by the register flip-flop 1 to send out its data. And then some time, which is the actual computation happening here, some logic computation, that is a combinational delay. And then, if you remember yesterday, we talked about setup time, which means some time required for the data to be ready before the edge arrives on flip-flop 2, which is edge number B. This is your overall path, and your accounting. So what is this whole timing checks? Timing checks are basically some form of an accounting operation for digital circuits. You're trying to account and check whether the whole operation happens in the given time or not. So in this case, the cycle time, whether the whole operation is able to fit in that. If it's going to take less time than T, great. And if that means you can possibly run faster because you have extra time available and you can shorten this. So the basic equation for you, or the inequality, is the cycle time, the time period, should be greater or equal. That means it's like inequality than the computation time. So sometimes people talk in terms of timing slack. What is timing slack? Timing slack means that if T is greater than this value, not equal to this value, then there is some extra delta available. That delta, which means you can reduce the cycle time by that amount, is called slack. That means you have some additional margin available. This whole computation is happening slightly quicker than the cycle time, which is good for you. So slack. So I'm now converting this inequality into an equality. How am I doing? If it is greater, then what the equation becomes is T is greater than this, which means T is equal to this quantity on the right side plus some slack, which is the extra value. You are fast, so you have some extra value available. And then we're saying this slack is nothing but cycle time minus this quantity, and this should be greater than or equal to 0 for the timing path to functional correct tree. That means you are able to meet the performance spec, or the clock is able to run at the right frequency. What is the right frequency? Since the time period is T, the frequency of this clock is going to be 1 by T. So if you are able to run at 1 by T frequency, for it to run at 1 by T frequency, slack should be greater than or equal to 0. That basically is the setup timing check. Any questions? Please type in the chat. Okay. Let's talk about hold timing, which is also called as a min timing. As I said, min timing is checking for not performance, and it's got no relevance to performance, but actually checking whether the data held by the sequential elements, the states held by the sequential elements, are correct or reliable or not. So there's no race problem in the design. That's what it means. As I said, hold timing, the other name for hold is race. Whether you're able to hold, which means whether you have a race problem or not. So hold is checking for race problems. So what race? Race means there is a, if this is your clock, as we saw earlier, data is being sent by this and being captured by this register. Sent on this edge, captured on edge number B. But hardware is sort of like a parallel system, right? The computation is all happening in parallel, which means even though we talked about edges A and B, it's a clock signal going to both the registers, which means there is some computation happening on edge A also for the flip-flop 2. It's not just that the flip-flop 1 is switching at A. Flip-flop 2 will also get switched at A because it's a rise edge. It's a rise edge flip-flop. because the clock is reaching this also, right? So which means there is a possibility, due to some weird reasons, we talked about process being fast, process variation, or due to some voltage having some issues, some PVT condition. We talked about PVT condition there, some condition, let's ignore that. Something which can make this path speed up, and which means on the edge A, when the flip-flop launches the data, and flip-flop 2 is also getting the edge A, due to some reason, the data launched from here quickly rushes in and gets captured by this 2. You want to avoid that because that is a race. What's a race? A race here is the data actually launched on, sent out on A edge and captured during the B edge. That is a valid data. But if there is a data launched by the A edge on flip-flop 1, but captured by the flip-flop 2 on the A edge itself, that's a race problem, or that's a hold problem, right? So basically there's a race between the right data coming one cycle later and the early data coming on the same cycle or the same edge. So edge A launches the data, it could potentially rush and be captured by flip-flop 2 on the edge A itself. That's a race, and we want to avoid that. And that's what hold timing is checking. As I said here earlier. So setup timing check is from edge A to B. Hold timing is on the same edge, same logical edge. So you want to ensure that this does not happen. Flip-flop 2 does not capture on this edge, which means this data launched by A or sent out by A should be captured only by edge B. It should not be captured by edge A. How will we know that edge A has captured it? We will be missing out on one data, which means there would have been some computation where there's some valid value which this register should have had on edge number A, but it gets overridden, or due to race, the new value of A immediately comes in, and we see that state being held by flip-flop 2 during cycle A, edge A. That's a race. We want to avoid that. So how do I avoid it? The way I can avoid it is I need to ensure that the delay of the data through the register, the clock to out delay, and the combinational stage delay, the logic delay, should be greater than the flip-flop 2's hold time requirement. If you remember, we talked about hold time means the time after the edge arrives on flip-flop 2, it needs to retain its old data for this amount of time, at least for the data to be valid or stable. That means from flip-flop 1, and since this is edge A, the data comes out from here on edge A. So edge A clock to out delay plus combinational delay should be going outside this window. It should be coming later than this. And if that happens, I will not have a hold time problem here. I will not have a race problem here. And that's a check. So clock to Q1 plus combinational delay should be greater than the hold time of flip-flop 2. That means it's coming after this time. So similarly, as we saw earlier for setup slack, since this is an inequality, I can convert this into an equality and I can get something which is a hold slack. Hold slack means I have some extra value, some margin is available. So if the clock to Q plus combinational delay is not exactly coming at this point, but coming well after this, then I have a hold slack. If it is exactly coming at this, this is called, this will be slack 0. So for the timing path to not have race issues or functional issues, hold slack should be greater than or equal to 0. So any timing check, I don't need to say slack should be greater than 0. Slack has to be greater than 0 for the timing or any kind of timing check to pass. Setup timing check, again, The check is it's a different type, but still again slack has to be greater than 0. Hold timing check, again slack has to be greater than 0, and so on. So any questions here? Did we understand what was described? Okay, so we will continue. So clock gating check. Clock gating check, again, as I said, I think we'll skip this. I think we'll come back and talk about this. I'm not sure whether the audience is following everything. We'll probably discuss this during the break if there is interest. I don't want to add some complexity at this point if there is some confusion about these two basic checks itself. So let me skip this, and if there is interest, please bring it up during the break, and we can talk about this. So one of the questions to ask is, we talked about all this timing. So how do you verify these delays or these timing checks or the timing problems are caught? The timing problems are caught by us before the digital design is taped out. What is tape out? Taped out? Taped out means it's before you send your design database to the foundry or the fabrication company, like TSMC or Global Foundry or even Intel, let's say, has its own foundry. So before they send it, the design, when we say it's design, it means before silicon comes out, or pre-silicon. So how do we catch these timing problems pre-silicon? So very simple, right? Some of them we talked about even yesterday. So you can run a functional simulation. One option is you can run functional simulation using Verilog or VHDL, where you have an extracted netlist, which the netlist could be in the form of Verilog or VHDL netlist, and you could run functional simulation. Like, for example, you may have seen tools like Model Sim, VCS, it's a Verilog simulator from Cadence, NC Sim, and all these functional front-end simulation tools. Basically, they work on the Verilog or the VHDL netlist, the extracted netlist, the design. And in this netlist, gate delays could be modeled as some worst case delays. We talked about arcs yesterday, some worst case delay arcs. For example, if it's a NAND 2, we can take the fall time of the NAND 2, and then if it's a NOR 4, we could take the rise time of the NOR 4, and we could take those delays, we can apply them as a transport delay on the gate when we're running these simulations. And similarly, we can also include the wire RC delay for the net as a transport delay. And then we can run simulations and we can capture some of these timing problems using that way. That's one way. Another is, we talked about the circuit simulation approach, which is using this tool called SPICE. Again, this has to work on the extracted circuit design, and it's also very accurate. This one is slightly an approximate. It could be very pessimistic, or it could be optimistic. But still, you could run some verification using this approach, or you could run a verification using this approach. SPICE is fairly accurate. It's probably the best way we could reliably run and understand the chip behavior before silicon comes out. So both of these approaches could be used. Now, as we discussed yesterday, we talked about some trade-offs. What do you think will be are the concerns if you're going to run a functional simulation either through VHDL Verilog on a extracted netlist or a SPICE on an extracted circuit netlist? What do you think are the problems? Do you see any problems, or do you think these are good approaches? And do you think this is what the industry uses? Did you understand the question? Yeah, what I'm trying to ask is whether these functional simulation approaches, do you see any concerns if you want to do some timing checks or delay verification using these approaches? Are there any concerns, or are these really good approaches which should work and we don't have any problems here? Yep, feel free to ask questions in the chat. I'll then understand if the audience is following the content being presented. Simulating for very little optimization. Bhaskar, can you unmute and explain what you're trying to say?
Sir, you asked about the functional simulation using SPICE.
Right. So do you see any concerns if we use that approach? Or is it a good approach?
Even though it's accurate, wouldn't it take more resources?
So it's a resource problem, runtime issues is what you're saying, or capacity issues. A lot of big machines are required, a lot of memory is required. Yeah, that's a basic problem with this. So you think that's something which we should avoid, or we don't have any other alternative?
I'm not aware of any other alternatives.
Okay, so that means if you're not aware of alternatives, this is the only approach that we could use, right? And that means if you are going to have a big chip, like even if it's a very simple microprocessor, let's say like an 8085, the Intel's first CPU. So which means you probably not the first CPU, but one of the early CPUs. You probably would be running a circuit simulation on that. That's still not a small chip. It had around 10,000 transistors, so or 5,000, certainly more than 5,000 transistors. That's like a lot of transistors to run simulations at. So if we don't have an option, that's the only way we can go. But people, as you rightly said, this is going to be extremely expensive because I need to run. It will take a lot of time because there are so many nets, so many devices, so many wires, resistance and capacitances, so many nets, nodes. So it's going to take a lot of time, which means you require a lot of memory, very big machines, too much memory requirement, and very fast machines because runtimes could be an issue, memory utilization issue, and depending on how long you want to run, the time taken could be a problem. Similar problem even here. So these two are not viable approaches, and people have clearly understood this. Not recently, but right from the earliest days. So we're talking about mid 70s, right from those days, people were aware of these challenges. And at that time, we didn't even have great CAD tools. So the functional simulation, right, is extremely expensive. When I say expensive, I mean you need to have large compute requirements, lots of machines to run the job in parallel, large memory requirements, runtimes are expensive, large, and then also, what do you do if you run all these simulations on the whole design? How would you be able to analyze it? Because there's too much data here. Sometimes even the analysis of the data itself is a challenge, right? So very less data is a problem, but just because you have a lot of data, a humongous amount of data also does not help you, because that again throws up the problem in the other extreme. How do you now analyze this data which is available with you, right? So these challenges clearly make these functional simulation approaches unviable. So what do we do? And what are other problems? Let's try to understand it. The points which I underlined here. Let's try to see if these make sense. So a specific design could possibly have many modes and scenarios. What do I mean by that? For example, there could be a scenario where it runs at high frequencies. There could be a scenario it runs at some blocks run at high frequency, some run at low frequency. There could be a scenario where, let's say, a small portion of the chip is running and not the whole chip. So many combinations are possible. So do we run all of them or a few? Again, the same problem. Now it's not just running one functional simulation, you have to run lots of them. The fact that one functional simulation itself is expensive, leave alone running so many simulations, right? So this basically means that even if, let's say, you're able to run a simulation, one functional simulation, now you're talking about running so many of them, and then how do you know which one to pick, right? Resources again becomes a problem. And then how do we know that all portions of the digital system are being tested by the simulation? Some portions may not be tested because, for example, there could be a specific combination of gates in such a way that certain nets in that logic may not toggle at all, or may not change. May always stay at 1, or may always stay at 0. So do we how do we ensure we are testing all these nets or all these scenarios? Does it matter? So these are some of the questions which people ask if, let's say, you're running functional simulations. So and then let's say you're able to run these functional simulations. What is the guarantee that your customer who runs some functional simulations which are not run by you? For example, let's say your chip is meant for Apple, and Apple is using it in its laptop, and Apple runs its own software, and that software may not be available with you to run the test. So how do you know that that functional scenario which Apple is running is relevant or not? So again, this becomes a problem. So that means that this whole functional simulation is just not viable because it's not just expensive, but also there's no way you are able to cover reliably the whole design. There could be so many possible scenarios and modes in which the design operates. You can't run all of it. And that's the reason why we have to find an alternative. And that's where the concept of static timing comes in. So what is done here in static timing? No dynamic simulation run. That means you don't run SPICE or Verilog VHDL simulations. No functional simulation. There's no switching based simulation happening. No dynamic simulation. And then the design, we don't look at the design based on its architecture. The design is broken into timing paths. This is one of the beauty of static timing. The fact that you can look at it just based on timing paths mean that it doesn't matter what type of design it is. Every design is identical. Identical in the sense that it's a timing path. As we saw earlier, we saw these timing paths. This could be a part of a design. And as long as this works reliably, I can say that if there is some data coming in here from the architecture, and if this path is meeting its timing requirements, at least this portion of the architecture is working reliably. Right? That's the beauty of it, which means you can do some sort of a divide and conquer. And all timing paths have a start point or end point, and start point and end points are usually sequential elements, flops, latches, memories, and so on. In some cases, there could be pins. And then combinatorial logic sits between the start point and end point, as we saw in that diagram earlier. And as I was saying, it doesn't matter what functionality exists in the design if you talk in terms of timing paths. We don't care whether some specific functionality is being covered by this combination logic or not. We don't care. When you're doing static timing, it doesn't matter to us. We only care about it as gates, and we only care about it whether the gates are between this start point to this end point. That's all that matters to us. And then one of the other real interesting and valuable aspect of static timing is the coverage of the design is complete. So even if there could be portions of the design which do not toggle due to architectural and functional reasons, but static timing can assume that it's going to toggle and it's going to propagate its timing arcs through that, assign some delays, and say, okay, there's going to be some setup timing and hold timing slack on this path. So because of all these aspects, static timing is a worst case analysis or a bounded analysis. Bounded means if you are meeting, let's say, setup timing with static timing, there is no way you're going to fail setup timing checks or performance max delay checks when you're running functional simulations, because this is bounding or worst case. Hence, the value or the success of this approach. So it came about in the late 70s. IBM came up with this approach somewhere in late 70s, and since then it just replaced all dynamic simulations and just become the go-to approach for analyzing timing in VLSI chips. I think a lot of you may already be aware of it, but it's sort of interesting or important to know what are some of the benefits or some of the aspects of static timing. Okay, so we are just in time. Reached the break 1. Let's open up for questions. Feel free to ask questions. I think it helped me to understand whether you are following what's been discussed. Do you have any questions from what we covered today? Any questions from the days prior to today's session? Do we have any questions? Is the audience clear about the basic setup, hold timing, and the advantage of static timing over dynamic simulation based approach? Okay, Chandrasekhar has asked about clock gating. Chandrasekhar, you want to unmute and be specific what you're looking for? Do you want me to explain clock gating, the timing aspects, or can you unmute and ask the question? Any questions from the previous topics which we covered over the last 4 days? Am I audible? It's not clear to me because seems like
Yes, sir. It is. You are
It's not-
audible, sir.
okay, that's good. So there's probably not much of an interest today. I don't know whether the topic is slightly confusing or difficult. I think if it is not very clear, I mean, you need to probably message or speak out so that we can, rather than going into too much of details into other aspects, we can focus on what we have covered and try to understand that well. So feel free to raise your questions.
Participants are requested to ask any clarification doubts.
Okay, so Shreyash asked the question. He's not clear about what is Slack. Shreyash, you want to unmute yourself and let's maybe discuss that. Do you want to unmute and talk about it?
Hello, sir.
Yeah. So let's talk about setup Slack. So Slack. Okay, what part of it was not clear to you? Let's see if we can put this in a better picture here. Let's see if I can do that. So let's say this is your cycle time, some box here. Okay. And you need to fit multiple things inside it. What are the multiple things you need to fit? That's a view of it. One thing which you want to fit is, let's say, clock to queue. Another thing you want to fit is what? Can you tell me?
Time.
Which time? The box is a time period. That's what you want. You want to fit everything within that. So if the box is time period, I have plugged in clock to queue as one of this. What is the other thing that I need to fit within this time period? Combinational delay. Does it make sense? And then I want to fit in what else? Can you tell me? Setup time. So I want to fit all of this in what? I want to fit all of this in this window. What is the length of this box? Can you guess? What is the length of this box?
No, sir.
That's your cycle time or the time period. So you're trying to fit all these things in one time period. The box, which is the base, is the time period, and you're trying to fit in all these things. What does fit in means? That the whole operation should complete. What are the operations? The register should send out its data from its clock pin to the output. That's clock to queue delay. That's this one. Let's give it some color coding if you want. Then we have combinational delay. And then what else? We have setup time. Do you see it now? So we have, this is probably, okay. So you have clock to queue, the red one, yellow, combinational delay, and then setup time. So when you fit all these things in, there is still some time left remaining in the cycle time. You see that brown portion?
Yes, sir.
That is the slack. That means there is extra space available in the cycle time. or extra time available in the cycle time. That time is called the slack. The fact that some extra time is available means the operation has computed quickly, and you can run at least this frequency. If, let's say, the box, let's copy the box on the top so that you can see that very clearly and fit it here. The length of the box is time period, as I said. So you're fitting in all these things. There's some extra space available. That's your slack. Now what happens, let's say that the cycle time was actually shorter. What happens? That means you are somewhere here, and the time taken by all these operations is taking more than the cycle time. That is negative slack, because you can only complete the operation in this window, but you have taken more time, you've gone beyond it. That means you are not able to complete the operation in the time. That is negative slack. That means this summation is greater than T, as seen here. Clock to queue plus combinational delay plus setup is, this whole thing is greater than T, and therefore you have no extra space available. It's going to be negative. And when is it going to be equal to 0? When is the slack equal to 0? What do you think? Where should I pull the box? Left or right? How much?
Right.
Right. And then till which point?
Up to setup time and completion.
Exactly. So it comes till this point. It's touch and go, right? It is exactly equal to cycle time. And that means both of them are equal, and the difference is going to be 0. And that is when slack is 0. So as long as it is 0, or the cycle time has more space available, you have some extra margin here in the cycle time, you can run at this frequency, 1 by T. So this is what setup slack is. Does it make sense?
Yes, sir, I understand. Thank you.
Similarly, you can do the same thing for hold slack, and any timing equation could be looked at it that way. As I was describing earlier, for hold slack, if you're coming just exactly at this point, which means clock to queue plus combinational delay is exactly coming at the point where the hold time is ending, slack is, what is the value of slack? Can you answer in the chat? If the clock to queue plus combinational delay is exactly at the coming at the point where the hold time is ending, the slack, hold slack value is how much, Harish? Harisha, actually, sorry, not Harish. What is the slack? Or Shreyas, I think since we talked about this, Shreyas, what do you think is the slack if clock to queue plus combinational delay is exactly coming at the point where the hold time is ending? How much is the hold slack? Shreyash, can you unmute yourself? Negative? No. Why is it negative? It is exactly at the point where this line is coming in. It's exactly at that point. At this point. That's going to be how much? It's going to be 0, because it's the whole clock to queue plus combination delay is equal to hold time, because they are coming at this point. So slack is 0. This means you are just meeting your hold time requirement, just avoiding race. And if the clock to queue plus combination delay is coming well after the hold time window, that means you are avoiding race very easily. You have a lot more time delay. You are pushing out the delay a lot more. That means in that case, the slack is positive. And in case you are coming within the window, inside it, slack is negative. That means you're going to have race issues. That's the whole idea. Hopefully this is clear to the audience now. Did everyone understand the concept of slack, hold slack, and the setup slack that I just described? Can you type in the chat if it is clear? Yes or no?
Sir,
Yeah, please go ahead.
hello. Sir, setup
please.
slack nothing but a required time minus arrival time, sir.
You can talk in terms of required time and arrival time. Required time and arrival time is specifically an STA2 terminology, right? So what you really need to understand is it's more terminology used by the tool, but the underlying concept is still basically what we discussed here. So the required time, what is the required time? Required time is going to be your cycle time, and the arrival time is going to be this delay.
Right? Then hold slack nothing but it's a reverse of setup slack, sir. Hold
it's not
slack.
reverse. It's not reverse because the cycle time is not here in the hold. But we want to, in the case of hold slack, we want to increase this delay. In the case of setup slack, I want to decrease this delay. That's the only difference.
Sir, slack increases means there will be race around condition will be more, na, sir?
No, slack is positive means I don't have race around problems. Why? Because this is the equation.
Negative means there will be race around problem, sir.
Yeah, any slack is negative, you have a timing problem. Yeah, if it's hold slack is negative, I could potentially have a race problem.
Okay, sir, fine.
Okay, so it's 8. We will resume from where we left it off. So how does STA work? I think we talked about this. I talked about static timing. So static timing analysis, which is specifically running a flow or a set of steps to static timing. So as discussed earlier, there will be sequential points, start point and end point, which means the timing starts from here, data is sent out from here, data endpoint means data is captured by this point, which means we want to, the equation has to be met between these 2 points, start and end points. There could be some number of gates or logic elements in the path, and this forms a timing path, right? So actually, a lot of this content is from Synopsys. You could actually go to Synopsys' website, and there's a lot of good content available. You can read about it, and I think try to understand. As we discussed, the basic concepts are similar to what we discussed, and I think there are a lot of other different checks also given on the website. If you understand some of the basic checks and you are exposed to some of the other advanced check, you can try to read through the material there. So I'll skip this. We talked about the setup check, but this is a good picture showing various possible timing paths. So let's look at assuming this is the design, let's say, right? There are pins A, clock, and this is Z pin. These are input pins, you have output pin. Clock will always be there in a synchronous design, as we discussed a couple of days back. Then clock is basically the control signal and determining all the registers which are controlled by that to change their states dictated by this signal, rise edge or the fall edge, depending on what type of register it is. And then you would have a lot of logic here to do some computation, some operation, and the design may look like this. We don't, and as I said, in the case of STA, we don't care what kind of gate or what functionality it's doing, because functionality is important only when you're running a functional simulation. But when you're doing static timing analysis, I only care about that they are gates and they have some delays, and I don't only care about that. So therefore, I don't need to know what's inside this. I only need to know maybe what type of gate it is and what delays they may have. And what are the different timing paths here? There's one possible timing path from a pin A to this register here. If a design has only pins, the pin could be treated as a start point, the input pin, and output pin could be treated as an end point. So that's a path here. Again, another sequential element sending out and interacting with this sequential element. That means there's a path here also. Is there a path from A, is there a signal reaching from A, the input side, and to this register? No, but there's going to the output. That means this could be a possible path. And then there's a path from this register to another register or a pin. Yes, so there's a path. So how many paths are there? A to this first flop to the second flop, the second flip-flop to the output, and then from the input pin A to the output pin Z. That way, the ST analysis would break the design down, irrespective of its functionality, into these paths. I'll skip this. We talked about setup and hold check. As I said, so hold check is a race check. You're checking the timing on the same edge. That means there's a race between what? On the second flop, there is a race between whether the right data, which was meant from the previous edge, is reaching, or whether the data coming from the current edge is racing with respect to this and reaching here. You want to block this and you want to ensure this. This is race, this is valid data. Setup check is ensuring that the valid data is captured and you're able to run at the right frequency. Race check or hold check is checking whether you are avoiding this data or not. And then how does STA look at some complex combination of gates like this? Let's say you have some inverter, some rearrangement and combination of gates which sort of looks like this. How does STA work? If there is a register here or pin here, and there's another register here or pin here, so which one will it pick? What is the worst delay here? The worst delay here is going to be the longest path. What are different paths possible? Inverter, this arc through, let's say pin on the top is A. So A to the output pin, that's one arc, and therefore this could be a path. Or you could have this inverter, this arc, and then you could traverse through here, this arc, then back, traverse through B pin to output, that could be an arc. Or you could have this path from here, this is the arc, traverses through this is the arc. So the first one is 2 stages, second one is going through 3 gates, third one is traveling through 2 gates. So whichever is among the 3 is going to have the maximum delay, STA is going to pick that. There's no guarantee that just because you have less number of stages, you're going to have smaller delay. STA doesn't make any assumptions like that. It'll actually calculate all the delays, 1, 2, and 3, and then it'll say, okay, among the 3, path 2 is the one which has the max delay. So let me consider that. But that's assuming that. So if you're considering only this pin to this pin, then between this path 1 and path 2, whichever has a higher delay, STA is going to pick that and drop the other path. It doesn't care about the other one. It takes care about, if it's setup timing, it cares only about the longest path. If it's hold timing, it's going to take the shorter path. As I said, hold is a min delay timing. It wants to cause, it's going to check for hold problems, which means you want to cause a hold problem, which means you want to speed up the data. So it's going to take a smaller path and so on. So that's how STA tool is going to work and pick the right path to choose for the timing check. So there are a lot of other checks we talked about. We'll just skip this. Clock gating is another one which is important. Not sure that the audience knows about clock gating, so I'll skip it for now. Maybe we'll talk about it tomorrow when we cover some power saving opportunities using clock gating. Or if there's any interest, please type in the chat. Okay, so we talked about STA analysis. Now, how does the STA flow will actually look like? So there will be an STA tool, which is sometimes also called the timer tool, the timing engine. There are multiple names you can use, which are used. And one example is, you may have heard about it, is prime time. Prime time is a STA tool or a timing engine from Synopsys. There's an STA tool, let's say prime time. Cadence has its own tool, which is called Tempus. So you could use any one of these tools. And then you need to pass some of these inputs for the flow to run. Parasitics. What are parasitics? Parasitics means you need to give information about the wire RC resistance and capacitance of various metals that are there, the unit resistance and unit capacitance values. And then based on the resistance, the wire that you have actually implemented in your designs for connecting various gates, it tries to calculate the R and Cs of those wire using this file. And then SDF. SDF means design conditions. What sort of delays are there on the pins? What's the clock frequency? Whether there is some transition time assumed on the signal pins. It's called the standard delay format. Then you need a netlist. Netlist is what is netlist? We talked about it. Netlist is basically an output which comes from the physical design flow. The earliest stage where we get the netlist is synthesis, where an RTL or a behavioral description of the design is converted into gate level thing, a physical connectivity of digital logic. So it needs a netlist, and the netlist could be coming from synthesis, or it could be coming from after placement or routing, any of these steps. And then you pass libraries, which we discussed yesterday. These are the .lib files. And then you have design constraints. The design constraints are again are basically describing things like clock frequencies and input pin assumptions, transitions. If there are mux logic gates, then what should be the select line values so that we determine which data is being picked and things of that sort. So it sort of sets some basic description of what's the right set of paths to analyze for STA2. So once STA completes, so there is a timing report. STA tool takes all these inputs, runs the flow, and it generates a timing report. A timing report captures a summary or details of the timing of the design. Let's say you run. There will be separate reports for setup, separate reports for hold. Clock gating checks will be captured in those reports, right? So the timing report may actually look like this. The timing report will have some information about what's the name of the start point, what is the name of the end point, some other details like what is the clock signal which is defined for that timing path, and path type. Path type max means setup timing, min means the hold timing. So whether it's a setup timing check or a hold timing check. And then this is the actual timing path. So there is a clock as shown in this diagram, and then you reach the register FF1. So from the clock through some delays, you reach this register. This register takes from its input clock to the output Q, it takes 0.50 unit delays. And then there's a buffer U2 on the path, which takes 0.11 delay. Another gate U3 on the path, which takes 0.11 delay. And then it reaches the B pin of the flip-flop. There is some delay here. Probably there is some wire delay here. And then this is the data arrival time. As someone was asking, there's arrival time and there's a required time and so on. This is the time taken by the logic and the launch flip-flop and the clock network reaching the launch flip-flop. And the data required time is basically what you need to meet. So clock reaching the capture flip-flop 2, and then the flip-flop 2, because it is a capture flip-flop, it will have a setup time. That means data should be ready before it. So you're taking the cycle time, the clock period, which is some 4 units, and then you are subtracting it, which means because the data has to be arriving before that time, and then the overall required time is if you add all these delays, is 4.79. So what it means is that the data arrival should be happening before 4.79. And if it is coming at 4.79, that's still okay. But in that case, it is just arriving on the capture flip-flop. So this difference, the data required time and the data arrival time in the timing report is called the slack, which if you remember in the equation that I showed, that's basically it's the same slack. But STA tools have a specific names which they have for these values. Data arrival time, which is when the data is expected to arrive. The data actually takes, and data required time is when it is expected to arrive. If this time is smaller than this, great. You are able to, you will be able to hit the desired frequency because the cycle time is being met. If this delay is greater, then that means the slack becomes negative. In this case, because this 1.87 is smaller than 4.79, obviously, therefore the data is coming in early than this required time, and hence I don't have any problem in meeting the performance. My slack is 2.92. This difference is a positive number. Any questions here? Did this make sense? Any doubts on the in this timing report? Is it clear to the audience? Anyone having any questions? Need some clarification? Okay, so we will continue. So we'll start talking about basics of some power analysis today. I think we're probably going ahead of time. I'll open up for questions. I'll try to cover this in the last 15-20 minutes maybe. So we have time today. We're almost half an hour. Do you want to ask any questions from today's topic or yesterday's or the previous days? Please feel free to ask questions. We are ahead of time. We can afford to spend some time us in the Q&A. Any doubts that you may have, anything you want to cover or discuss from the previous discussion that we had.
Hello, sir. Harun, sir.
Yes, sir.
Yeah. Tomorrow, because they have to take a test, sir, between around 8 to 9 o'clock. Okay. So probably tomorrow you can take only for the 1 hour, sir, between 7 to 8 o'clock.
Okay.
Okay, because they have to take a one test around 30 questions. We are prepared already with respect to what we are done in the you are done in the last 5 days. Based on that, they have to answer for 30 questions. We are planning to give that test around between 8 to 9 o'clock. So that's why the second session of today, if possible, talk with respect to the tools, sir. what are the tools we can use for with respect to the either maybe the back end or the front end?
Tomorrow?
Today it is possible, sir.
So today I don't have slides, but I think maybe what I can do is tomorrow I can try to cover those open source tools you wanted to discuss. Maybe I can try to.
First 1 hour you can talk about the tool, sir. Then later after 1 hour we'll take the feedback. Today, as usual, as per your schedule, you can carry, sir.
Okay.
Okay, sir. Okay.
Yeah. So Veena, you had a question. Do you want to unmute and ask what exactly you mean?
Is the slack time depend only on path, sir?
Slack depends only.
Longest path, shortest path.
So
Like
yeah, the setup timing depends on the on the longest path or the path having the maximum delay. The whole timing depends on the path having minimum delay. But when obviously these delay, I mean, it depends on the path, yes. But each of these path delays are also dependent on what type of other conditions exist. For example, what is the process variation, whether it's a fast process, slow process, and so on. It depends on what is the voltage. So the PVT corner will matter. But for that specific PVT corner, yes, it depends only on path.
okay, sir. Thank you.
Yeah. The audience is not very active today. Not sure why, but hopefully it's not because of the topic being covered. And if it's not very clear, please let me know in the chat, and I will try to address some of your questions or doubts. But staying muted is not going to help because it's neither helping you nor me to understand whether you need any help or not. Don't feel shy. Please either type in the chat or unmute yourself and ask your question. Okay, I think at this rate, looks like we will probably complete early because there's probably not much of a response from the audience. Then I think we'll try to quickly finish this and we will end today's session early. So let me try to talk about part. Yeah, please go ahead.
Sir, can you tell me the difference between the dynamic timing analysis and static timing analysis, sir? Which is the accurate compared to that one, sir? Why? Because in static timing analysis, we are not considering that logical path, sir. We are doing that combinational circuits and we are finding that. Which is the best one, sir, compared to this?
So we talked about this earlier. So let's maybe go back to those slides. I talked about the benefit of
DTA versus STA, sir. Dynamic timing analysis versus static timing.
Yeah, so when you want to do a dynamic analysis, you have to run some sort of a functional simulation, right? So this functional simulation is going to tell you very clearly whether you're going to have whether the functionality is correct or not, which is great, and you get to know all the details of the design. But the problem is that there is no guarantee that this requires a lot of computational resources, a lot of machines, a lot of memory. You need to have the runtime will be very, very long, and you cannot run this if you have a very, very big chip. lots of transistors, lot of logic gates, and so on. That's the reason why STA is the best approach for running timing analysis, because even if you have a really very big chip which could have millions of gates, STA people run this frequently, almost every day. Companies run this. When you have millions of gates, they're able to run timing on that. So the only problem is that STA is pessimistic. Why pessimistic? Because that's the whole idea of how it's been set up. And so in some cases, STA could actually be telling you that the frequency is slightly lower than what is possible on silicon, but that's okay. It's unavoidable. That's the cost you have to pay to not run functional simulation. So in comparing dynamic timing versus static is invariably the best approach. If you have a very small circuit and you can afford to run simulations there, then go ahead and run SPICE or some circuit simulation and then get the precise numbers. But you cannot run this for a large design, and that's where static timing analysis comes in.
Okay. Sir, in static STA, we are using only for the smaller designs, sir, compared to DTA.
No, STA, no. DTA dynamic is only for small designs. STA is going to be for huge designs, for full design.
Okay.
It is static, right? Static means you don't need to worry about functionality.
Yes.
It is not switching, which means it can be fast, very fast.
Okay. Okay, sir. Thanks.
Okay, so let's talk about some power consumption basics. We'll touch upon this briefly. So you obviously would have studied some of it in your textbooks, in your coursework. So in CMOS logic, the power can be split up into two categories. One is dynamic, that means when the circuit switches, that means it changes state. And another is static, which means irrespective of whether it's changing state or not, it's always drawing some power. So static power and specifically the leakage power. Leakage power is when basically when you have, as we saw in one of the earlier presentations, when you're trying to build a static CMOS logic, you're going to have a pull up and a pull down network, and only one of these two networks are active, which means that the path from supply to ground is always isolated. But even though, let's say the path is isolated, in reality, when you're building a real electrical circuit, there is no way you will not have some very high resistance path from the supply to ground. So the switch is not ideal. It has some leakage current. So it will be very high resistance. It's in cutoff, but there will be some small current flowing through it. That small current makes up the leakage from the supply to ground, but it is very small. It is almost like 1 millionth. It means 1 by 1 million a factor of the dynamic power, and it could be even smaller depending on what type of technology it is. But since you have million to billions of gates in the design, all of those terms add up, and this number could become significant at a chip level or at a big design level. Therefore, that's where it starts becoming very critical. Dynamic power is always critical because this shows up when we are switching, and this is a significantly large current compared to leakage. And if it's a signal like a clock which is continuously toggling and switching, the dynamic power of that is fairly high. So dynamic power can be broken into two types: switching power, that means when the output is changing state, and the short circuit power is when in between we are changing state. Very, very brief period, depending on the input signal transition. Both the PMOS and the NMOS are in the saturation state. So since both of them are on during that period, you have a current flowing for a very brief period, when as the input is switching from low to high or high to low, both the transistors are on for that brief period, there's a short circuit path from supply to ground, and that makes up this current. And switching power is really the power required to change the state of the output capacitor or the load. So this is how we can categorize the power consumption of a digital CMOS logic. Now, this is a very basic thing which I think you may have read. So the dynamic power, or sometimes called as switching power, is nothing but the activity factor. We'll talk about what activity factor is if you're not already aware of it. Just ignore this for now. Think of it as 1. So it depends on F clock or the activity of the input signal, the load, the output load capacitance, and the supply. So C V square F. This is basically the power consumed from the supply for you to cycle through one round of power up, power down in a CMOS logic gate. So power up, power down, because every CMOS gate has to power up. That means draw power from and change the state of the load from low to high, and then again it has to discharge for one cycle of operation to complete. And then that one cycle operation for a CMOS logic gate is CV square F. Now, what is this AF and what is activity factor? Now, activity factor is something where, let's say, a design is running at some clock frequency. As you saw, if it's a sequential design, you're going to have a clock signal, so that it's running at some clock frequency. So what is done is that we use the clock frequency as reference to define the activity of all other signals in the design. And since we're using clock as a reference, so and to define the activity of all other signals, so there is a term which is called activity factor, which represents the rate at which any signal is switching versus the design's clock. The ratio, that ratio is activity factor. If the design, if the input is switching at the same rate as the clock, activity factor is 1. If the input is switching at half the rate of the clock, the activity factor is 0.5, and so on. So let's take this example. If it's a clock signal, because it's being compared with itself, activity factor is going to be 1. And if it's a digital signal, let's say, which is running at half the frequency of the input clock, right? Its activity factor is 0.5. What does that mean? It means that if I take one cycle of the main clock, or if I take this signal and if I take it through its full cycle, which ends here, starts here and ends here, in this window, how many clocks can I fit in? I can fit in 1 clock period, 2 clock period. That means I can fit in 2 clock cycles in this one cycle of this. Therefore, activity factor of this is its time period divided by how many cycles you can fit in one cycle, and that basically makes it 0.5. And if the clock was running at 1/4, if the digital signal was 1/4, its cycle time was 4 times the clock, then the activity factor would be 0.5, because I can, in that one cycle of the digital signal, I can fit in 4 clock cycles. So which means it's going to switch infrequently. The smaller this number is, the more infrequent it's going to cycle between high and low. The more it is closer to 1, the more frequently it's going to toggle, and its activity is approaching the clock of the design. So that's where this activity factor term comes in, and that's where you have this alpha, sometimes also called as alpha, activity factor alpha, CV square F. F is the frequency of the design. So we talked about short circuit current, and as I was saying, short circuit current shows up only when there is a transition in between happening on the input signal, not when it is stable. So in between, when you are transitioning, NMOS turns on and PMOS is also on. So you have a path from here to here for a very brief period as the signal is changing state, that current from here to here is the short circuit current. And therefore, if you multiply by supply, you get the short circuit power. Now leakage, there are multiple possible leakage. So this diagram is showing leakage. So let's take the input signal is 0. This is an inverter, input signal is 0, which means which gate is off and which is on. 0 means PMOS is on, NMOS is off. So NMOS is behaving like an open switch, but it never behaves like an ideal open switch because it will have not infinite resistance, but some very high resistance, but certainly not infinity, which means there's effectively some current path which is possible even though the current is going to be very small. This current from supply to ground, this open or off transistor makes up the leakage. And if it is input is 1, obviously PMOS is off. So you basically have the leakage set by the PMOS. So this leakage, this is the leakage which is the current flowing through the channel. This is called the subthreshold. Is basically called the subthreshold leakage. Why subthreshold? Because the specific device which is off is having its gate voltage versus the source voltage below the threshold, or not meeting its threshold voltage requirement. So therefore, this leakage current which is flowing through the channel is called a subthreshold leakage. I have not shown in this diagram other form of leakage. The other forms of leakage which is possible are, there's a leakage which is potentially possible from this logic 1, which is going to be some VDD through the gate, because there's an oxide here. There's some very high resistance here, but because there's very high resistance, the current which can possibly flow through this is going to be very small, but still it's possible through this and then coming to the ground. That's a gate leakage. That's a possibility that there's a gate leakage which can happen like this. In this case, there's a gate leakage which can happen from the source, and then there's a low potential here, which means a very low current because the oxide is there and its resistance is very high. Very low current is going to come towards this side and drain here, and that means this can make up a gate leakage. There's no gate leakage for this scenario for the NMOS because 0 and 0. There's no gate leakage on the PMOS side because 1 and 1, but gate leakage is for the NMOS here, gate leakage for the PMOS here. So subthreshold leakage or the channel leakage when the transistor is off, or the gate leakage are two forms of leakage. There are additional forms of leakage, which when you look at the full transistor structure, you will have some diodes, reverse bias diodes, which are there. I haven't shown them. I think we can probably take a look once you look through some textbooks. You can look at the transistors detailed view. You can form some reverse bias diodes between the junctions on source drain to the substrate, and that, if it's reverse bias, will form some leakage current there. So these are the three different forms of static leakage contributing currents. So this is the equation of the subthreshold leakage. Subthreshold leakage, as I said, was basically the channel leakage going from the source to the drain when the transistor is off. In this case, it's going to be NMOS, and in this case, it's going to be PMOS. So the current flowing through the channel source to drain when that transistor is off is called the subthreshold leakage. So subthreshold leakage equation is this, some complex term here, and there are a lot of technology variables as we've been discussing, mobility, oxide gate capacitance, threshold voltage, and then this is a design parameter, the gate to source voltage, a system parameter, the width and the length, which sort of depends on technology, which is L, and width, which is your parameter, the design parameter, and then VTH, this is your thermal voltage, this quantity, and the some other additional variable coming from technology. So that's sort of a very fairly complex equation, and this is a fairly significant concern in some of the latest technology nodes. Leakage makes up a big percentage of the overall power consumption of a chip. So we can run some power analysis flow. Once we have the timing libs, as we discussed yesterday, the timing libs can characterize power also. And then you can run the static power dissipation analysis, dynamic power dissipation analysis, and then the design could say, okay, I'm meeting my power spec, or I'm not meeting my power spec. My dynamic power is meeting spec. Let's say it's low. The leakage power is high. I need to do some optimization. We'll talk about optimization methods for power savings and timing improvements tomorrow. So that's where I think we'll end today. Let's take some questions if there are. I'll open up for questions now.
So participants are requested to ask any doubts if you need any clarification regarding today's session.
Okay, I think if there are no more questions, then we'll end it here.
Okay, Arun Nair, sir. We will close the session today. Thank you very much, sir, for your valuable session. So tomorrow we will start at 7 o'clock with the first hour session by Arun Nair, sir, then followed by quiz. So all the participants are requested to join tomorrow at 7 o'clock. Arun Nair, sir, shall we close the session, sir?
We can. I think if there are no more questions, I'm available. But the audience seems to be not active today. So we have a question from Deepika. Deepika, you want to unmute and ask the question?
Sir, what happens when leakage power decreases in any circuit, sir?
So when you say leakage power, you mean static leakage, right?
Yes, sir. Yes, sir.
So when the leakage power decreases, it's good. I mean, I didn't understand the question. When you say leakage power decreases, it's always good, right? The power is lower. Do you have any specific query, or like what you're trying to what you have in mind. It's not very clear to me what's the point you're asking here. So if power is lower, it's always good. So there's no
What
problem there.
about the delay in that cases?
What about the delay in that case?
Yes, sir.
But you have to understand. Okay, so are you doing some optimization of the gate or the timing path that is resulting in the leakage reducing, or the leakage is low right from the start? If you're doing some optimization, let's say you're using some design techniques, let's say something called as a high BT transistor, you're introducing high BT logic gates you're using, that could reduce leakage. So whatever you do to reduce the leakage also slows down the transistor or slows down the gate. So if you have done something like that to reduce the leakage, or you reduce the supply, as we saw in this equation, the leakage also depends on the gate source voltage, which is nothing but the supply voltage. So any of these methods where you have either increased the threshold voltage or you have decreased the supply voltage would result in the circuit slowing down. So if you have done that method and using that you have reduced the leakage, yes, the circuit could slow down and you could have some timing issues because of that. Not necessarily, but it can possibly happen. Does that answer your question?
Yes, sir. Yes, sir. Thank you, sir.
Okay. So Sri Lakshmi, you want to unmute and ask?
So what's the use of timing report, sir? By using timing report, can we reduce the hold time, sir?
So timing report is like a audit report. You know what's audit, right? For example, companies do audit. What is STA? STA is basically some kind of an audit report. Audit means whether you are meeting all your requirements properly or not. So it's a report which is dumbed out by the timing tool, and it tells, when you read that report, you check whether all the paths have at least zero slack or not. So if all the paths have at least zero slack, so good. So the timing is all met in the design and it's meeting its specs. You would be able to run at the right frequency. You will not have race issues, and all other timing concerns are met. So timing report is primarily for that. It is for the user or the designer to go and check. It is basically telling you that this is the state of the design when it was when you ran ST on it. Can you reduce hold time? No, hold time is something which comes from the circuit. Let's say, for example, if it's a flip-flop that you've designed, its hold time is something which is already defined by that circuit. Unless you're going and modifying that circuit, you may not be able to change the hold time from a timing report. One way you can artificially do is not from the circuit, but something like you can add some extra delay on the clock path, or you can add some extra delay on the data path to slow down the data path, or add slow down the clock path. That is possible, but that is not actually changing the hold time, but that is more like a design method to fix the setup time or the hold time problems. Okay. Does that answer the question? You
Can
have
we
any?
design a circuit after preparing timing report, sir?
Can we?
Sir, can we design a circuit after preparing a timing report so that we can reduce, no, sir?
So normally that is not done. Why? Because see, once you start your execution, which means you started designing, you don't want to change your inputs because it takes a lot of time to verify the inputs. And for example, let's take an example, right? So if you're building, let's say you're running a catering business, and you have decided the menu for the day, and you decided what you're going to have. You bought all the ingredients, and suddenly you find that you want to change the menu, or you want to change something. That's going to be disruptive, right? You have decided and you spent some effort, you planned it, you sort of bought some ingredients, you decided how much time you're going to spend. So just like that, for example, if you build some circuits for a chip, and you don't go to a timing report and then come back and say, I'm going to change this. If it's a very small design, you can do it, but if it's a very big design, usually that's not done. So some of these circuits are designed early and we can have some very tight specifications for them. We can say that, okay, this circuit should have a very low hold time, let's say 0 time, or a negative hold time, and we can design it that way. So as long as I can have some tight specifications, I can take care of a problem, even if the timing report says that I'm going to have issues. And even if the timing report says that there's a problem, I can go to the design and fix it, but I don't need to change the underlying circuits.
Thank
Okay.
you, sir.
Okay, I think if there are no more questions, we'll just end it here. Thank you, and we'll meet tomorrow.
Thank you very much, sir. And
Thanks.
thank all the participants. So tomorrow at the same time, 7 o'clock, we will join. Thank you all.